So first off, if you want the slides, they're available here. That should be RMF, just so you know. So you don't have to take any photos or excessive note-taking if you want to follow along or look up after the talk. So this will be a fairly technical, or given the other talks, technical presentation where I try to describe in a sort of a high-level way what deep learning is and why it's a powerful method, and then also give you sort of a flavor of what how you actually use a deep learning and what it does, and when you train a model, what tends to happen. So first of all, then why is deep learning such a buzzword right now? And the deep neural networks that underlie a deep learning model have actually been around since the 60s, so it's not really a new idea. But two key enablers has been the amount of data that is available, which has been of paramount importance in giving them enough data to generalize from so that they don't overfit. And the second one has been the increasing compute capacity, and specifically in terms of GPUs, which tend to give us this sort of the capacity to train this model in a reasonable amount of time. So the sort of deep learning wave that we're in right now started in 2012 with the deep learning model winning the ImageNet competition with a sort of crushing margin, almost cutting the error rate in half. And ever since, that error rate has been cut in half by a new deep learning model. They grow increasingly large and increasingly deep. When we talk about deep learning then, we have these sort of three core components that make up that concept. And the first one is this deep neural network, which is a chaining of very simple computational functions, like a linear function with a non-linear sort of element-wise function that you apply to it, and then you can stack this into these very deep models that can do very many things. And in order to train them, we use something called backpropagation, which is mathematically just the chain rule of differentiation, so not very fancy in itself. But what's really powerful is that because the model chains together these simple mechanisms, we can use automatic differentiation to get the derivatives, meaning that you as a researcher, you only write what the model should output, and then you get the derivative automatically, basically for free. So you don't have to sit and think about how to update these parameters. And that gives us extreme flexibility in what we can actually model. The sort of core concept then that makes deep learning a powerful paradigm are modularity, end-to-end learning, and distributed representation. So what I mean by modularity is this compositionality. We have a few very simple functions like linear algebra, some element-wise nonlinearities, and by combining them in different ways, we can basically build a model to represent anything. There's this universal function approximator theorem for deep learning, saying that they can approximate any function. End-to-end learning then is the idea that, or the fact that when you have these types of models, you can, rather than you have this data, you have to do some feature engineering, and then you put a linear regression on top or something like that. You can build the entire pipeline as a trainable model that you use gradient descent to optimize, and you get this sort of end-to-end framework where you do some light pre-processing from raw text to say integer like one-hot encoding, and then the model itself will extract the features it needs on top of the classifier or whatever prediction algorithm you have on top of that. So in the example here in the image, they train a model to take an image as input. Then they have one sort of lower layer stack that extracts features out of that image. And then they have a decoder that takes those features and tries to build a representation of the semantic meaning of that image. And then finally they put a decoder on top of that that will generate a caption for that image. And rather than train all of these three models in separation and then try to fit them together, this is trained end-to-end in a single training loop. Distributed representation sort of goes into that in that when you do this sort of automated feature engineering, you learn not the features, but rather the feature space. So you get a sort of meaningful space where similar concept will be grouped close together, so it will become very compact rather than sort of this big messy space that you don't really know what to do in. And because of that, you get better classification performance, or really performance on any task. So I'll very briefly just give you a flavor now on sort of the details on the mechanism, what we mean by backpropagation and what we mean by training a neural network. And so the key idea then is you have this model. In this case, in the top row, you have the feed-forward network, which is an affine transformation followed by an element-wise nonlinearity, such as the sigmoid function or the tan function or something like that. And then during backpropagation, we take the partial derivatives with respect to the parameters and with respect to the input, and we sort of keep them around in some cache. And then when we stack these modules together into a deep neural network, and we want to get the sort of the update rule, in the end you get a loss. You do a prediction and you get a loss, like if you use mean squared error or if you use maximum likelihood. And you can then backpropagate this loss through these partial derivatives to get a measure of what the partial sort of, or the marginal effect of each parameter is, if you were to increase it a bit or if you were to decrease it a bit. And that gives us the sort of the signal of what that parameter should be, in which direction it should go to decrease the loss. And by doing this iteratively, we ultimately converge on some local minima. So this is some pseudocode in PyTorch, just to give you an idea of what this might look like when you do this as a researcher. So this code here on the right specifies the feed-forward model. So you have the parameters W and B. And then the only thing you have to write out is the forward computational graph. That's how you go from input to output, how you get your predictions. And then when you train the model, you have some data set that can be arbitrarily large. That's not really a problem in deep learning, because we use mini batches that can be maybe 20 samples, 100 samples. Depends a bit on the problem that you have. And then for each of these mini batches, we generate predictions by running the model in the sort of forward graph. We compute the loss. And once we have the loss, we have this graph also that goes from the loss backward to every parameter. So we can run the model backward to get the gradients. And when we have those gradients, we can apply gradient descent to update our parameter in the direction that makes the loss go down the most. So this is a greedy algorithm, and generally we won't ever reach a global minima, but this, for some empirical reason that no one really understands yet, it doesn't seem to be a problem. So most of the local minimas in a deep learning model are actually very good in terms of generalization. So this is typically what a training process would look like. You have this training curve in red and then the validation error in cyan. And because these models are so powerful, training error isn't really a very useful metric. They will always go down. The more data you give them and the longer you train them for, it'll just go down to 0 at some point, because these models can actually memorize even random data. If you were to randomize the labels, it would still get 0 training error. The validation error, on the other hand, at some point you're going to overfit. So you have this sort of typically called an early stopping criteria, where you stop training once your validation error isn't improving anymore. So there are a few tricks to the trade here in terms of getting these models to train as fast as possible and to be sure that they converge to something good. Stanford has some really good online courses. Coursera does as well, if you want to sort of see what those tricks are. Some good sort of pointers are to standardize your inputs to make sure that you don't get very large weights. As I said, look out for the overfitting. And a good thing also is to look at the gradients. One thing that's worth mentioning here is, so you might have heard that deep learning requires lots and lots of data. And that's true if you train it from scratch. If you take if you initialize your parameters randomly and then you want to train it, you typically need tens of thousands of observations, if not millions. But what you can do is you have a problem that, say, require some sort of image processing or natural language processing, is you can take a pre-trained model, something that perhaps Google has spent a few months training, and then you can fine-tune that to your specific problem. And in these cases, because the raw information, the raw structure of, say, processing an image or natural language is already in the model, you only need something like a few hundred observations, or depending a bit on the difficulty of the problem. But so the idea that you need lots and lots of data isn't actually true anymore if you use transfer learning techniques. So it's good to know in social science. So being a bit more sort of perhaps applied, there are, apart from the feed-forward layer that I just showed you, 2 core sort of architectures that we use. And then by combining them in different ways, we get new models that we apply to the problem that we have at hand. And one of them is the convolutional neural network, which was the one that first sort of gave us the deep learning breakthrough. And the convolutional neural network was designed or sort of motivated specifically for processing images. And what they do, instead of having this large matrix that you do vector matrix multiplication with for an input, you have a fairly small kernel. So in this image, this example here, you have a 3x3 kernel, and then you slide that over your inputs. If it's an image, you would do it over the matrix, and if it's a vector, you would do it over that vector. And by doing that, you encode two sort of inductive biases. The first one is that you want to have local invariance. If I were to move this cat around in the image, I still want the model to understand that it's a cat in the image. So it doesn't really matter where the cat is in that image. And the second one is we have some sort of, the locality doesn't, if you take a small slice of this cat, then the probability that the pixels are going to look roughly the same is fairly large. So you can sort of aggregate them into these sort of more aggregate features. And in the same way, in images, typically, you don't have this sort of global dependence. You might have a cat in one space, but that doesn't really tell you anything about what's going to be in another space. So having this kernel sort of slide through that image gives us a very good inductive bias. You can also use these for if you have high-frequency data, like if you have financial data, something like that, in which case you would do sort of aggregation on a very short frequency basis. However, typically, if you have sequential data, you would use a recurrent neural network. And a recurrent neural network is just, if you take a feed-forward layer and you were to unroll it through time, you get this very deep feed-forward layer that you can't train as it is. But if you share the parameters across time, you get a recurrent neural network. And these are extremely powerful models. So these are actually, if you have a background in computer science, equivalent to a neural Turing machine, or a Turing machine. So they have capacity, at least, for infinite memory. Now that you have these sort of key elements, the feed-forward layer, the convolutional neural network, and the RNN, you can combine them to fit your problem in basically any number of ways. There's no limit to what you can model just by combining these things. And you don't really have to care about that much as well. You just write out how you go from input to output, and automatic differentiation will take care of the gradient updates for you. Of course, that doesn't mean that your model is always going to converge, so you have to be somewhat intelligent in how you do these designs. And to give you sort of a flavor of what you can do, if you take autonomous driving, for instance, how those systems work is that you have a convolutional neural network that take the input, that is an image or a sequence of images. It will then sort of try to get features out of that in some abstract way. And then when you have those features, you will take an RNN that will go through all of these images, and it will decide how to change the steering direction or the velocity and etc. based on the features extracted through that image. And if you were to train this system one component at a time, it would be extremely difficult to get them all to play together. But because it's deep learning, you can train it all as one system, end to end, and you can get a car that drives itself. Let's see, 13, right. So in terms of social science then, deep learning is not really the model of choice perhaps at this time, but it's starting to creep up in a number of areas, and I think it's going to show up a lot more in the years to come. And one of the reasons is that there are lots of data sources that actually have the size of the data that we need to train a model from scratch. So Twitter feed would be in one example. You also have streaming data and all these sort of things that gives us information about social systems that do give us a lot of data. The other one is that as we grow smarter in how we can train these models and understand them better, we actually don't need all that much data anymore, and we can apply them to problems where that sort of data requirement might not even be true anymore. Having said that, there are of course some caveats to using deep learning, one of them being the problem of understanding just what they've learned. So causality is a major issue in sort of inferring that in these models. But in terms of understanding patterns in sort of complex data, these are by far the best models to use. And yeah, I think that's it.